Okay, let's continue with naive Bayes lecture. Okay, topic 6. I hope you recall from our practical class that I mentioned about the posterior distribution. Okay, by using Bayes' theorem can be written as a form of likelihood function multiplied with the prior probability divided by the distribution of the data x. Okay, so this is similar to the idea used behind linear discriminant analysis. Okay, the main difference is for this likelihood function, also I also call it a conditional probability. Okay, so this thing here. Okay, in naive Bayes is assuming that x1 to xp are all independent. Okay, that's why we can break it. Break the conditional probability or likelihood function into this form. Okay, and then we have a proportional relation like this. Okay, so finally, by using something similar to linear discriminant analysis, we are able to find out the output, the response of our target. What is the most likely class it's going to be based on this argument. Okay, so this is part which is different from the linear discriminant analysis. Okay, here again we use take logarithmic calculation, which is the thing used in computer calculation. Okay, it's for this whole topic, for hand calculation purposes, we didn't apply this formula, as we'll see later on. Okay, so for the prior distribution, right, it's something rather simple. It's just basically using counting. N is the number of rows. Okay, in order to illustrate this, I'll just continue with the simplest case where one of the column is actually categorical. Okay, so it has this when it's categorical, it's just a matter of counting. Okay, so the easiest way to look at all this formula, together with the variation of the form of formula used yesterday. Not yesterday. In the practical class. Okay, we just look at an example. Okay, this is a past year exam question. So it has 3 columns: x1, x2, x3, and y is output or response or target. Many names for it, right? Okay, so the output has is either positive or negative. Okay, categorical data. Others are also basically categorical data. Okay, we are asked without using the Laplace smoothing, to predict the response. Y based on these observations. Okay, so we are given x1, x2, and x3 where we need to predict. Okay, is this thing difficult? Okay, it should be rather easy. So the way to do it is, first we want to find the prior distribution. Okay, so for y, right, based on what I mentioned just now, we let p be positive, n be negative. Okay, then let's look at the case when it's positive. So we have 7 rows, right? 7 rows. Okay, and we only have 4 positive here. You can just count number of positives. So that's why the prior distribution for y when it's equals to positive, it's 4/7. Okay, similarly for the negative case is 3/7. Okay, now because we are given x1 equals to b, x2 equals to yes, and x3 equals to 1, right? So that's why we don't need to consider all other possibilities in x1. Like x1 actually has a, b, and c, isn't it? Okay, and for x2 it's yes or no. Okay, here says yes. That's why you'll find that here in the conditional probability we just calculate the case when okay, given y equals to positive, okay, when x1 equals to b, x2 equals to yes, and x3 equals to 1. Okay, what are the probabilities? Okay, which is basically just counting, because okay, y equals to p, there are 4 possibilities. Okay, four of them, and out of these 4 positive we can count that there's only 1 b, that's why it's 1 over 4, and 2 yes for x2, that's why it's 2 over 4, which reduces to 1 over 2. And okay, we can find that there are 3 1s here, that's why it's 3 over 4. Okay, and the posterior distribution okay, is proportional to, okay, yeah, just the multiplication, right, which if you care to look at the formula over here, okay, it's formula 6.3, right? It's just a product of them. Okay, so yeah, okay, let's continue. So that's why it's a product. Okay, similarly for the okay, I just use abbreviation here, so which means y equals to n, right, negative case. So okay, we can just calculate this 2 out of 3, 2 out of 3, and 1 out of 3, okay, corresponding to the x1, x2, x3. Okay, so yeah, okay, this should probably be a capital X, right? Okay, so never mind. Okay, here is just the simple product of them, and we find that this is much larger than this, so that's why not much, it's larger than it, so by comparison its high probability of it is higher. Okay, so I mean, since you have played with the practical class, okay, you want to see is it possible for you to use what you learn in the practical class here. Okay, so just show you. Okay, is it easy? The answer is no. Okay, so let's have a look at it. So the data frame is the same. Okay, it's just a matter of putting all the tables there. Okay, over here. So okay, I can open up something to run it. Okay, I'll probably run it here. Run it. Okay, execute. So if I just show you the, okay, you can see that, okay, it's the same as the table over there, okay, with abbreviation. Okay, so what we need to be careful is the third column is actually numeric because it's a form of zeros and one. In order to use naive Bayes, okay, to handle, we have to transform it to factor. That's why we need this command here, okay, to change it to categorical data. And after that, I'll just be creating a model, okay, which is without any smoothing. Okay, so it tells me that there are 0 probability happening. Okay, so that's why, okay, theoretically, if it's other cases, I might be in trouble. So but for this thing, there's no 0 here, as we can see, so no issue. Okay, you can print the model out. It will display quite a lot of things. Okay, I'll just move over here and show you. okay, model. Okay, you can see that the prior probability, okay, just is given here, right? Priori or prior probability, right? Okay, is the same over here, 4/7 and 3/7. Okay, yeah, just to show you, I'll open up another thing here to show you. Okay, so it's 3/7 and 4/7, right? Okay, so we can see, yes, it's an exact match. Okay, so yeah, let's turn this thing off. Okay, and then we find that, okay, all this probability is calculated. Okay, what I want to point out is this thing, it tells us there is a 0 probability of seeing it in n for when y equals to n. Okay, so that's why we have a warning there. Okay, so when we are looking for x1 equals to a, right? Okay, the probability will always be equals to 0. Okay, in some sense it's unfair, right? Okay, so this is the model. So now we want to do the prediction. It's not a simple task because when we actually just create a data frame, okay, we can apply the class function, right? Okay, new data with class to check what are their data type. Okay, it tells us it's a factor, but we have to be careful because if we check the levels, right, of data of the new data x1, we will find that it only has one level, so we need to change it to follow exactly the levels which is found in our original data frame. So that's why we need this tree. Then only we can go and calculate the probability and also the class of the, okay, based on our input, right? Okay, everyone can see this is the input, something we want to predict. Okay, so finally we can just show the output, okay, which tells us okay, the y, right, is predicted to be output to be negative, right, with probability of this thing. How come we are not seeing this in our calculation? It's because if you go and key in this is our estimate, right? Okay, and then you try to calculate this thing in the ratio, okay, and you will find that these two more or less matches, okay, because we have been using rounding, okay, that's why it won't be an exact match.